Hi, I'm Nick Sanford, and I'll be presenting the dynamically controlled infrared linear to circular polarizer. This particular project, we're working in the infrared spectrum at about 11 micrometers wavelength, which corresponds to about 27 terahertz. And we use that window because it has relatively low atmospheric losses. And also using the infrared band, any illuminator, kind of like an infrared flashlight, it won't be visible to the naked eye. And this is also a band that has relatively low water vapor absorption in a band that's compatible with CO2 lasers. The advantages of using polarization are well known. They clean up images, get rid of glare, they help to see through water, light, rain, fog, things like that. And they also help to see through smoke. Infrared also has similar advantages that with the longer wavelengths, we can see through things like cloud cover and bad weather. The first polarizer I'll talk about is the dual circular polarizer and linear polarizer. This particular polarizer has two modes of operation. The first mode of operation is just a standard polarizer, like a wire grid polarizer here that has energy, that the energy will come in and pass only vertical polarization. But when we add an electrical bias, the polarizer, it changes modes. It'll act like a circular polarizer or a quarter wave plate. So it'll convert the vertical polarization into circular polarization. The structure shown here, we have a glass base and a plasma etched glass rails. So we take a piece of glass and we etch away these slots and we fill these slots full of liquid crystal. And then we put a glass lid on the top of that. And both the bottom and the top of this have an ITO layer, which is indium tin oxide layer, which is a transparent conductor. And when we put a voltage bias on that conductor, it changes the characteristics of the liquid crystal that's trapped between the layers. And what that liquid crystal does is when we leave it open, the molecules will orient horizontally and we have a relatively high dielectric constant. Then when we add a voltage bias, they orient vertically and they have a lower dielectric constant. In the IoT kind of acts like a capacitor that pulls an electric field in there that changes the orientation. So with this, the polarizer has two different modes to it. When we put the liquid crystal in there, the index of refraction of the liquid crystal is about the same index of refraction of glass. So it just kind of looks like a solid sheet of glass. But when we remove the voltage bias, then the index of refraction of the liquid crystal increases, and that increase causes circular polarization. It converts the vertical polarization into circular polarization by having a slow axis and a fast axis inside the polarizer. Here we see the configuration. We see an electron microscope image of the structure with the grooves in it. So here are plasma etched. So these are plasma etched away and filled with liquid crystal, and the lid is put on it. And here we see an HFS simulation of that, the pink showing the liquid crystal and then the glass covering the remainder of the device. And here it is. So we refer to it as an active quarter wave plate. In the first mode, with the voltage bias, the linear polarization comes in. And again, the liquid crystal has the same index of refraction as the glass. So the polarization just passes right through the structure unperturbed, but with no voltage bias. Now the index of refraction of the liquid crystal is significantly higher than the glass around it in the unit cell. So it converts that as a fast axis and a slow axis, and it converts that into circular polarization. Here we see the performance again, the vertical axis in the dB in the horizontal axis is the frequency in terahertz. And we see the different sections of this. There's some reflection off the structures. So this is the vertical pole that is reflected back, and there's some cross-polar energy that is reflected as well. There's some attenuation loss in the liquid crystal and glass. When you combine all these losses together, you end up with this yellow curve that is about 9 dB down. So that's about 12% of the energy lost due to the reflection and attenuation loss. And the rest of it is passed as circular polarization. Now for the second type of polarizer, this is the active dual circular polarizer. This particular polarizer takes in vertical polarization and puts out either right-hand circular polarization or left-hand circular polarization, depending on the bias. And this type of polarizer deployed some reflective grids. So unlike most polarizers, when the polarization comes in, of course it passes one polarization, but rather than attenuate the other polarization, burn up as heat, these are highly conductive and they reflect the other polarization away, so it can react with other layers of the grid. So here we see the configuration. The energy would come in through the bottom here, and then it sees the wire grid, and then the next wire grid, and eventually it comes up to the liquid crystal layer in the gaps held by these microbeads, and then sees a final layer of gold grid here. And you can see the relative dimension of these layers. So when we have no voltage bias, here it so there's no ITO layer. We just put a voltage bias directly on the wire lines to the bias the liquid crystal. Here we see the performance. We have a linear polarization coming in through the bottom. And when there's no voltage bias, it goes through here. Has these multiple reflections and eventually generates right-hand circular polarization coming out the top. And when we add the voltage bias, the linear polarization comes in here, goes through these multiple reflections, and then you can see the polarization already forming here, coming out as a left-hand circular polarization. Here's the performance again, right-hand circular polarization with a bit more loss than we had in the other configuration, because the copper does have some attenuation loss at these frequencies. Some of the power is turned into heat due to that finite conductivity in the copper, but again, relatively low, maybe 15% of the energy is burned up in attenuation. And we can see that approximately, that's approximately true for both right-hand and left-hand polarization states. Great, so thank you for viewing my presentation. I look forward to seeing you at the conference.